On June 30, 1908, something exploded over Siberia with enough force to flatten roughly 80 million trees. Yet when investigators finally reached the center, they found no crater. That missing crater is not a flaw in the cosmic object explanation. It is one of the strongest clues. The leading explanation is that the object exploded in the atmosphere, creating an airburst before it could strike the ground as an intact body. Tunguska is often introduced as a mystery about what hit Earth. A better question is what the evidence can actually distinguish. The forest records the blast, but not a neat label saying asteroid or comet. The event is therefore both solved and unsolved. The physical type of disaster is well supported. The exact altitude, energy, diameter, and composition remain estimates. The explosion occurred near the Podkamennaya Tunguska River, in a remote region of central Siberia. People in the wider area reported a brilliant object crossing the sky, intense heat, and shock effects powerful enough to knock people down and shake buildings. Those reports matter, but they are not instrument readings. Their accounts establish a violent atmospheric phenomenon. They do not provide a precise altitude or a measured diameter. An incoming cosmic body meets denser air as it descends. Pressure and heating increase rapidly. If the body breaks apart and releases most of its energy above the surface, the atmosphere carries the blast downward and outward. The ground is struck by a pressure wave, not necessarily by an intact rock. That distinction explains the central contradiction. A ground impact excavates material and builds a crater rim. An airburst can devastate a huge area while leaving no single impact bowl. Tunguska's missing crater points toward where the energy was released, above the forest. Direct scientific investigation did not begin immediately. In 1927, Leonid Ko-Olik led the first major expedition into the remote region, 19 years after the explosion. The photographs used in this episode come from those later expeditions. They show investigators and the damaged landscape years after the event. They are historical evidence of the aftermath, not photographs of the 1908 fireball or the instant of explosion. Ko-Olik expected that a large meteorite might have struck the ground. What his teams found was stranger. Enormous areas of trees lying in related directions, as if the forest had been pressed outward by a force centered above the landscape. The expedition also found an inner region where some trunks still stood. Their branches had been stripped away, while forests farther out had fallen. That pattern is consistent with a powerful pressure wave descending more steeply near the center and pushing outward at greater distance. Every fallen tree was a rough directional marker. Across the region, tens of millions of damaged trees created a pattern far beyond an ordinary local event. The pattern was not a perfect compass drawing. Terrain, tree strength, and local conditions complicated it. But the broad radial arrangement allowed investigators to work backward toward a central region even without a crater, a surviving vehicle, or a recovered object large enough to explain the devastation. Near that center, the standing stripped trees supplied another clue. A blast arriving from above can remove branches while leaving some trunks upright beneath it. Farther away, the pressure wave travels more horizontally and has greater leverage to push whole trees over. This does not turn every trunk into a precision sensor. It turns the forest into a combined record. Direction, density, and distance matter together. The evidence becomes persuasive because many observations point toward the same kind of event. Ko-Olik searched boggy terrain for the expected impact site, but no conventional crater appeared. Small depressions could be examined and debated, yet none supplied the unmistakable bowl, displaced rock, or central projectile expected from a major ground impact. Meteor Crater in Arizona shows the other outcome. There, an object reached the ground with enough remaining mass and speed to excavate a visible crater. That photograph is a comparison, not an image of Tunguska. At Tunguska, the incoming body apparently failed higher in the atmosphere. Its motion and fragmentation converted energy into heat, pressure, and a rapidly expanding shock wave. The forest received the destructive result even though the ground did not receive one intact crater-making body. Models commonly place the burst several kilometers above the surface, but the exact altitude is reconstructed, not directly measured. The same caution applies to energy estimates. Many megatons of TNT conveys the scale. It should not be mistaken for a single instrument reading. The object's diameter is also inferred from models of entry, breakup, and damage. Change the assumed material, speed, or angle, and the estimate changes. A useful explanation, therefore, gives a range of possibilities instead of pretending that one exact size was recovered from the forest. An asteroid fragment is often proposed because rocky bodies commonly enter Earth's atmosphere. A comet fragment has also been proposed because a more fragile, ice-rich body could break apart high above the ground and leave little large material behind. Neither label is required to explain the basic damage pattern. Both hypotheses involve a natural cosmic body entering the atmosphere and releasing enormous energy before a normal ground impact. The forest can strongly support an airburst while remaining less decisive about composition. This is an important evidence lesson. Confidence does not have to be all or nothing. Investigators can be highly confident about the event type, moderately confident about a range of burst conditions, and still uncertain about the exact object. The absence of a large surviving fragment does not erase the event. Airbursts are destructive precisely because an object can transfer its energy before reaching the surface intact. What remains is the physical response of the atmosphere and the landscape. Tunguska showed that a cosmic hazard does not need to carve a crater to produce regional devastation. The atmosphere can become part of the impact process, converting an incoming body's energy into a blast that reaches the surface over a vast area. It also showed why evidence must be read at the right level. The date, location, damaged area, treefall pattern, and missing crater are observations. Burst altitude, energy, diameter, and composition are reconstructions with different degrees of uncertainty. The answer to the thumbnail is therefore simple. An atmospheric airburst flattened the forest. The deeper answer is more useful. A missing crater did not make Tunguska inexplicable. It revealed that the explosion happened before the object reached the ground. Next, the archive turns to Apollo 13. The oxygen tank explosion is famous, but surviving it required engineers to solve a chain of problems that began only after the first blast. The next episode follows that evidence under pressure.